Today we are joined with Dr. Nathan Wiebe, who is going to talk to us a little about methods of simulating quantum dynamics. And just to give you all some background about him, but before that, I just want you all to know if you have any questions after the lecture, please use the raise hand feature, or you can type your questions in the chat. So Nathan Wiebe is a researcher in quantum computing who focuses on quantum methods for machine learning and simulation of physical systems. His work has provided the first quantum algorithms for deep learning, least squares, fitting, quantum simulation using linear combination of unitaries and quantum Hamiltonian learning, near optimal simulation of time-dependent physical system, efficient Bayes phase estimation, and also has pioneered the use of particle filters to characterizing quantum devices, as well as many other contributions ranging from the foundation of thermodynamics to adiabatic quantum computing and quantum chemistry simulation. He received his PhD from the University of Calgary, did a postdoc at the University of Waterloo, and is presently faculty in the computer science department at the University of Toronto. I'd like to welcome Dr. Nathan Wiebe. Nathan, it's all yours.
Wonderful. Thank you very much. All right, let me just make sure I still got my mic on. Can you all hear me?
Yes.
Excellent. Great. So thank you very much, everybody, for making it. Today, I'm going to be telling you about something that probably has been the biggest focus of my career so far, which is simulating quantum dynamics on quantum computers. And one of the things I really kind of want to impart on you is that in the last couple of years, we've seen a monumental progress in the hardware side. I'll be honest with you, Google and IBM are making quantum devices right now that I thought I would realistically see at the end of my career, not kind of at the early phases. And despite that, that isn't the only area that we've made a lot of progress in. Within the last few years, actually, there's been enormous progress in quantum algorithms. In particular, mostly in quantum simulation. The advances that we've made in quantum simulation are actually so radical that within like 5 years ago, that was the first time anybody ever showed an estimate for the number of gates that would be needed for simulating chemical dynamics. And the reason why it took that long is because every time somebody tried to do that before, the number was so stupidly big that it just seemed like it wasn't even worthwhile continuing the rest of the calculation. And since then, we've managed to actually improve it by a factor of 100,000 over a course of 4 years. So this is a radically changing area of quantum algorithms. And on top of that, many other quantum algorithms, such as linear systems algorithms for optimization, such as solving semi-definite programs, all of these end up actually depending on Hamiltonian simulation subroutines. So the way to look at this is if you're interested in the basic sciences, this is really kind of fundamental because it allows us to understand, in some sense, what the computational power of nature actually is. But if I put my computer scientist hat back on again for a second, then there's another reason to be interested in this because it gives us a fundamentally different approach for compiling algorithms down into fundamental gate operations that are more general than even just dynamics. But let me just get started on this. So the key idea behind quantum simulation, or the main reason why I think most people are interested in it now, is just because of the fact that it promises exponential speedups for a wide range of problems on a quantum computer. To give you a little bit of an idea, the first algorithm that was provided for this. Thank you very much. My wife is giving me some reinforcements. All right. So The first algorithm that was actually proven to have a super polynomial speedup over the best known classical algorithms was, of course, Shor's algorithm for factoring. But factoring actually only solved a very narrow range of problems. Simulation, on the other hand, is incredibly broad. What we can do with simulation is we can do all sorts of things, ranging from finally having a hope of understanding the mechanisms behind high temperature superconductivity to cracking the reaction pathways behind photosynthesis or biological nitrogen fixation. And those are just all the direct applications for it, let alone the other ones that I mentioned. And so this is one of the reasons why advances in quantum simulation actually are kind of now front and center for quantum computing, because of the fact that it gives us hope that once all the communications that have been sent across the internet using RSA have been cracked, that there will still be uses for quantum computers down the line. And so to give you an idea about how quantum simulation works, I want to begin with like my biggest pet peeve about quantum simulation, which is, of course, the name. Yes, how can you tell I'm an academic? Because of the fact that I'm most annoyed by the name of my field. But the reason why I'm annoyed by it is that I think that if we'd had good wisdom beforehand, we would have called it quantum emulation. The main reason for that is because of the fact that quantum computers are universal. And what that means is that any unitary transformation that could be performed on the quantum bits inside the quantum computer can be approximated with an arbitrarily small error by a discrete gate sequence on the quantum computer. Now, quantum dynamics, at least for closed systems, is described by a unitary matrix. And so what that means is that any physical dynamics that we're interested in governed by quantum mechanics can be approximated on a quantum computer. And this approximation is kind of gives the quantum computer a way of emulating the physical system. So in this sense, it isn't kind of like we do on our big supercomputers right now, like Summit, for simulating something like chemical dynamics. There, what we do is we have like an in silico solution to what the result is. It's stored in a bit string. That bit string is very, very different from the molecule that we're trying to simulate, which looks nothing like a bit string, obviously. In a quantum computer, though, the wave function that ends up describing the quantum bits, in some sense, is logically equivalent to the molecule we're trying to simulate. But all the measurements and all the operations that we end up performing on the quantum computer are physically equivalent to an experiment that we could have performed in the lab on that exact same molecule. And that's why quantum simulation is really more of an emulation, because you're kind of tricking the quantum computer into thinking that it's a molecule. All right, so just to give you an idea about how this works, time evolution in quantum mechanics is given in the form of e to the minus iht, where h is this matrix known as the Hamiltonian. Now, if you have n quantum bits, or kind of like in a physics sense, n subsystems in the part that you're dealing with, the dimension of this matrix is enormous. This matrix would be 2 to the n by 2 to the n. So if you're looking at solving this for n is greater than 100, you're not looking at solving this directly, because a 2 to the 100 by 2 to the 100 matrix, best of my knowledge, at that scale, you would, even if you turned the entire universe over into a giant silicon-based computer, you would not actually have enough mass in order to build enough RAM in order to store that. But interestingly enough, that actually describes a relatively small quantum system that could be only like 100 interacting electrons. So the real question is kind of like, how does nature do it? And quantum computing gives an answer for it. The basic idea is that this unitary e to the minus iht, where again h is this Hamiltonian or energy operator, is what we want to build in order to describe the dynamics. So there's kind of like in simulation 2 worlds that we need to think about. There's the world of the physical system that we want to simulate, and the world of the quantum computer. And I've described these 2 worlds with 2 different boxes. Now, the observant amongst you might realize, hey, wait a second, how come the quantum computer's box is bigger than the physical system? Well, the reason why is because there could be extra bits of information that we use along the way to make the quantum computation faster. So because of the extra memory that quantum computers have, generically, they'll actually occupy a bigger space than the space that the physical system would have occupied by itself. Okay? So the idea basically is, imagine you've got some initial quantum state, psi naught, that you prepare. Now, the time evolution of that initial state will take you to a final state, e to the minus I ht psi naught. Now, this is what happens in the physical world. What we want to do is we want to be able to create a correspondence between each of these states in the physical world and bit strings, or quantum bit strings, in the quantum computer. Then this dynamics that I drew from this red curve going down the side over here becomes equivalent to some other potentially strange dynamics that the quantum computer experiences when you're applying all of the gates, all the discrete gates that you are using in order to approximate e to the minus IHT. The hope is, though, that when you do all of these transformations, that you end up in a final state that is equivalent, logically, to a state that's within distance epsilon with the actual state that you would physically see in the world of the physical system. So that's basically it. What we want is we want to be able to map the dynamics described by e to the minus IHT over to the quantum computer and describe that dynamics within error epsilon and for any evolution time t using as few gate operations as possible. Okay, so that's the game. Make it as accurate as possible, do it as long as possible, while making it as cheap as possible. All right, so that's basically it. Now, again, putting my computer scientist hat back on, you can actually end up thinking about this problem as a compilation problem. So the central challenge behind all of this is to build a sequence of quantum operations that the quantum computer knows how to implement in its instruction set. Things like rotations, controlled not gates, things like that. And we'd like to be able to build that. But the challenge is that we don't explicitly know what U of t is. Well, why do I say that? Well, the reason why is, like I said before, if H is describing 100 interacting electrons, then this is a 2 to the 100 by 2 to the 100 matrix. And there ain't no way you're going to exponentiate a 2 to the 100 by 2 to the 100 matrix. So we're trying to build this U of t, but at the same time, we don't know what U of t actually is. So it's a weird compilation problem where we're trying to compile this target, but we don't formally know precisely what the target is explicitly, only implicitly through this equation. And so because of that, it's kind of obvious that if I tried to brute force it, that isn't going to work. So the way quantum simulation algorithms end up working is by breaking up this problem of implementing e to the minus IHT into a series of subproblems that we know how to simulate. And there's three broad strategies. And for the observant amongst you, you'll notice that I put 4 things down over there. I'd like to say that was intentional, but apparently there's 3 types of mathematicians, those that can count and those that can't. And so the three and a bit strategies that we end up that have kind of become popular in recent years are Trotter-Suzuki formulas, randomized evolutions, which were invented by Earl Campbell in quantum error correction a couple of years back, that are now known under the more catchy name of Q-drift. There's linear combinations of unitaries, which were invented by myself and Andrew Childs, but kind of have really been perfected in the last couple of years. And there's also quantum walks, which were invented by Andrew Childs, but were kind of perfected by Guanghao Lo and Ike Schwang. So these are the kind of general strategies for doing this. And what I'd like to do is I'd like to give you some intuition behind how each of them works. The main reason why I want to do that is that something that a lot of people in the field don't realize is that none of these strategies actually are strictly better than each other. That's why I didn't say new approach for quantum simulation as the title of my talk. Because if there was one, if there was the one method to rule them all, then that's what we would do. Forget all these other approaches. I'd just be telling you about that. Each of these have different pros and different cons and should be used under different circumstances. And so I want to give you some intuition for what those circumstances are and show you some applications of particular types of problems that have structure that expose themselves very well to some of these different techniques. So the first one that I'd like to talk about is Trotter-Suzuki simulations. And I realized there's one major problem with this slide. The major problem is I don't tell you what a Trotter-Suzuki simulation is. So let me now use the handy-dandy power of PowerPoint to explain how we do this. So let's say what we've got is this is our unitary, right? We assume for these simulations that our Hamiltonian is a sum of HJs. And each of these HJs is taken to be simple, okay? I'll leave out what I mean by simple for the moment, but let's just assume that it's a sum of simple pieces. The Trotter-Suzuki approximation ends up saying that the sum over AJ, H sub j t, is equal to the product over j, e to the minus I, AJ, there should be a j here, HJ t plus order t squared. Wonderful. Okay, so that's the idea behind the Trotter-Suzuki approximation. So what it says is that if you've got a sum of these different terms, up to error that's small, if you pick t to be your time step to be sufficiently small, then you can approximate the exponential of the sum by the product of exponentials, okay? And I should say more properly, this actually ends up going like order t squared, kind of the max commutator of hj, hk. So if all of the terms commute, then there's no error whatsoever in this approximation. But in general, there's going to be some error that we can make arbitrarily small. So what this ends up saying is basically, if we have a method for implementing each of these terms individually, well, then we can do the sum just by building this sequence up one by one. So that's the whole idea. Now, the question is, what does simple mean, right? How do I find a bunch of individual terms so that I can build a discrete quantum circuit for this over here? The broadest family of simple terms that we know of right now are called one-sparse Hamiltonians. And a one-sparse Hamiltonian, I gave an example of one down here, which is this matrix. By one-sparse, what I mean is that there's at most one non-zero matrix element in every row and column. And this sounds, again, like it's also maybe a little bit too CS-y for many physics people here. But I want to remind you that this definition actually covers most of the relevant classes of Hamiltonians that we usually describe physical systems with. For example, here's a spin model, which actually could also be used to describe two electrons interacting on nearby sites. This over here, is a sum of different Pauli operators. Each of these tensor products of Pauli operators are one-sparse as well. So basically, just about all of chemistry simulation, it turns out, is actually already written as a sum of one-sparse matrices. So this is one of the things that makes chemistry such a nice target for simulation, because basically the chemists have already done our work for us. So to give you an idea about what makes this one-sparse structure easy to simulate, what I've done is I've helpfully colored in all of these individual blocks. So let's imagine what happens if I was to take this matrix and square it. Well, what would happen is I would take these diagonal elements and I'd multiply them through by themselves, right? Then with the off-diagonal elements, I'd multiply, this by this and put it in there. And basically, it would end up filling up, if I took repeated powers, the blue shaded blocks, but never go outside of that. So if I went to like h cubed, h to the fourth, it'll always stay inside this blue block. Similarly with the gray block, it's all going to end up staying in there. So upon exponentiation, each of these individual blocks remains fixed. So if I want to be able to simulate the dynamics of just this green block, I don't need to know what's going on in the salmon block or the blue block or the gray block. I only need the green block to understand how the green block evolves. And so what this means that what we can do is we can build a brute force quantum circuit for handling each of these individual blocks that computes all of the information that's needed for that block and doesn't compute the rest. And then what that ends up giving us is this gives us a general kind of like a block simulator. And the idea is that if you feed in psi block over here into that block simulator, you're going to get e to the minus I hj t psi block coming back up. And because quantum mechanics is linear, what this ends up meaning is this is the profoundly amazing part of this. The profoundly amazing part is that if we have u acting on, say, psi j, aj over here, that is equal to u acting on sum of j, aj, psi j. And believe it or not, this is actually the origin of the exponential speedup. The simple, stupidly obvious fact that because u is a linear operator, it can be brought outside of the sum. That is the origin of the exponential speedup. The reason why is it says, okay, well, normally you'd imagine if we had a subroutine for correctly doing the dynamics of each block, I'd have to first do it to this block. Then I'd have to do it to that block. Then I'd have to do it to that block. Then I'd have to do it to that block. Now, if there's an exponentially large number of blocks, I'd have to do an exponentially large number of steps. But linearity means that actually, if we write one that works for any block, we can apply it to all of them at the same time using quantum superposition. And that's how we can do an exponentially large number of these simple operations all at once. So it's actually, believe it or not, the linearity of quantum mechanics that ends up giving us our power here. So that's how Trotter-Suzuki formulas end up working at a high level. Let me give you a much quicker introduction to linear combination of unitaries. So linear combination of unitaries, it kind of began at the end of my PhD back in Calgary. I was sitting around wondering, you know, I know how to multiply two unitary matrices on a quantum computer, but how the heck would I add them? I didn't have anything in mind for why I'd want to add them at the time, but I thought it would be, you know, just a kind of a cool side project to work on and figure out a way to add them. Well, it turns out that you can, and this technique known for it now is known as a block encoding. And the basic idea is that what we want to do is the sum of unitary matrices isn't something that a quantum computer can do naturally. Because, for example, if you just added identity in poly Z, you get a projector, and that ain't unitary. So the sum of unitary matrices ought not to be something that you can do natively. The trick is, what you do is you say, well, although I can't do the sum of the unitaries directly, I can build the sum of unitary matrices as a subblock of a larger unitary matrix. And that's the whole trick. So if I want to do u plus v, which might be not unitary or not, I encode that as a subblock of a larger unitary matrix, and I call this a block encoding. Now, again, the perceptive amongst you might notice, hey, wait a second, you know, dude, you didn't fill in all those question marks. Actually, that was intentional in this case, unlike my three simple points earlier. This is, in this case, we don't actually care what those values are for this, this unitary. Because if we want to add u plus v over here in this subspace, we don't care what it does in all of these error subspaces out here. So all we need to do is build a unitary that does the right thing in this subspace at the top and might fail horribly in some uncontrolled way everywhere else. But giving us this freedom for the matrix to be radically different in all these other blocks makes the compilation challenge a lot easier. In fact, actually, this is how we solve the problem in general. If we want to have a matrix that we could write as a weighted sum of these unitaries, then we can build this using a quantum subroutine that I call uprep, which prepares from the zero state a sum of all of these coefficients that you want to prepare for the Hamiltonian terms. Then what you end up doing is you end up getting building another circuit that for any index given in a quantum register J, what it does is it'll apply that corresponding term u sub j to the state. Then once you've got built those two operations, then you can create a block encoding of any matrix B using this simple sequence of 3 unitaries. So this is how you can do literally any linear algebra, actually, on a quantum computer with some success probability. You rephrase it as this. Now, this has gotten pretty abstract. What does this have to do with quantum simulation? Well, going back a bit for this mess, remember that I said that e to the minus iht can be expanded through its Taylor series in this form, right? Let's imagine that h was, just for simplicity, unitary. Then e to the minus iht is actually a sum of unitaries in that case. And this discussion that I gave over here gives you a way of building a sum of unitaries. So we can use this technique in order to implement the Taylor series up to some finite order of e to the minus iht. And that's how the simulation method works. This, combined with a form of amplitude amplification to boost the success probability, i.e. the probability of starting in this block, applying this unitary, and ending in that block, is 100%. So that is the key idea behind linear combination of unitaries. Final and fanciest approach for this is qubitization, which is a quantum walk-based approach. Now, this quantum walk-based approach, what it does is it does the following. So just to give you an idea, the circuit that I gave down here with select and prepare, these are literally the same uprep and uselect operations that I discussed over here. So the circuit for building this walk operator that we're using here is really simple. It's actually just 3 of those unitaries that I've described over here. Now, if we take a look at the Hamiltonian in its eigenbasis, what it ends up looking like is, just a diagonal, right, of its eigenvalues, just by the definition of eigenbasis. So if we exponentiate it then, and I've absorbed the time into the eigenvalues here, I apologize for that. I make no apologies for h bar though. And once we've done that, we have e to the minus I lambdas up here. It turns out when we build this walk operator is equivalent up to an isometry that is like a linear growth of the space. It's equivalent to the original matrix, but instead the eigenvalues are replaced by the arc sign of the original eigenvalues. And so the whole idea then is that what you do is you need to come up with a method for transforming the eigenvalues of this simple circuit down here into the original eigenvalues of this. And this is one of the kind of recent profound techniques that we've come up with recently, which my colleagues and I have named the quantum singular value transformation, which gives us a way of literally transforming the eigenvalues of a unitary into anything we want. So what we can do with this is we can implement the sign, like transform the eigenvalues of the walk operator into the sign of those eigenvalues, undoing the arc sign and mapping the spectrum of W into the ideal spectrum of U that we want to build for the time evolution. And there's 2 ways that we can do this, either using linear combination of unitaries, using some trick known as the Jacobi-Unger expansion, or using quantum signal processing, which we now call the quantum singular value transformation, or view as a particular case of that. So this is how qubitization ends up working. Now, if you pay attention to nothing else during this talk, I recommend paying attention to this incredibly ugly slide, because this ugly slide is really the stuff that you needed to know from all of that overly long discussion that I gave you. Key thing is, out of these 3 main strategies, Trotter-Suzuki methods have some really nice pros and cons. Their huge pro is that they require no extra qubits. So, like if you recall this diagram that I had with the 2 worlds, right? In the case of Trotter-Suzuki simulations, this right box is the same size as the left box. There's no waste space whatsoever with that approach. Furthermore, it's very nice because of the fact that the error ends up scaling like the commutators of the Hamiltonian terms. So if the Hamiltonian terms mostly commute, the error is 0. However, we don't end up getting optimal scaling with T or the air. With linear combinations of unitaries, we, on the other hand, get scaling that doesn't depend on the commutators, but we end up getting logarithmic scaling with the error tolerance, which is much better than the subpolynomial but not polylogarithmic scaling that we get with Trotter-Suzuki methods. And its biggest pro is it's very flexible. It's the most flexible out of any of these methods and works for time-dependent simulations as well as time-independent simulations. Qubitization, on the other hand, actually has provably optimal scaling. Actually, you can show that if you were able to beat this scaling, then there are particular query problems that you could solve on a quantum computer faster than quantum mechanics allows. So this scaling that I end up giving at the top is the fastest scaling you can generically have without taking advantage of the structure inside a problem. So qubitization kicks ass from that perspective. But there's some downsides. It needs a lot of ancilla, maybe not as many as LCU, but it really doesn't work for time-dependent Hamiltonians. Is in like I've bashed my head against the wall for ages trying to figure out how to get this to work. And everything I've tried has failed. Everything everybody else has tried has failed. And so this idea doesn't seem to map over to deal with time-dependent Hamiltonians. And that actually is kind of important, increasingly important, because of recent work that Guanghao Lo and I did that showed actually that something really kind of amazing ends up happening if you simulate a time-dependent Hamiltonian. It turns out that if we use these linear combination of unitaries to simulate a time-dependent Hamiltonian, and that case would occur, imagine if your AJs were now AJ of T, okay? So it's now changing either slowly or quickly in time. The amazing thing about it is that the cost ends up kind of still scaling like the maximum value of AJ of T, but it doesn't depend on its derivatives. So you could have a Hamiltonian that's with terms that are rapidly oscillating. And that rapid oscillation, it doesn't affect how long it takes for the quantum computer to execute it. So this creates an opportunity because what you can do is you can do a frame transformation. If you have a really big term in your Hamiltonian, what you can do is you can go into a rotating frame of that really big term. Now, this term, which might have dominated the sum of the magnitudes of the terms that you have here, now is going into a very fast rotation. And the fast rotations are essentially free in the simulation model. So basically, we can take the biggest term of our Hamiltonian and just kill it. And this, for systems that are dominated by one particular interaction, ends up causing the linear combination of unitaries to still be the best approach. And actually, in some cases, can give you an exponential improvement over the quote-unquote optimal qubitization simulation. So this is why this is a great triumvirate of simulation methods and not, qubitization for the win. So now, in the remaining time, I want to go over some applications because I said each of these different strategies has different cases when you want to use them and different cases when you won't. So in order to be able to use them best, you really kind of have to know what types of problems end up exposing the structures that you want to take advantage of. For example, if you've got one term that's really dominant, you want to use LCU. If you've got really nice commutator structures for your terms, i.e. things are really local, for example, or you want to do it in a memory-reduced way, Trotter-Suzuki is your guy. But if it doesn't have any self-evident structure to it, then taking advantage of the optimal scaling of qubitization is likely what you want to do. So I'll show you examples of cases where we choose to apply preferentially Trotter-Suzuki as well as qubitization. So the first example I'm going to show you is simulation of quantum electrodynamics. And for you nerdy field theory types, I wrote the Lagrangian up on top because I know you'll be angry at me if I don't write a Lagrangian somewhere. But the Lagrange, basically what the Schwinger model ends up describing is it ends up describing quantum electrodynamics in 1+1 dimensions. And the way that this can be reformulated using the Kogut-Susskind formulation into an effective Hamiltonian that ends up looking like the following. So in this Hamiltonian view, what we have is we have alternating sites. that correspond to positronic orbitals and electronic orbitals with a gauge field. You think of this as like the electric field, linking these two together. And all the interactions basically between the particles are mitigated by Gauss's law effectively. So what we end up having here in this formalism is we end up having that the energy of this particular configuration is the electric field energy, which we've written here as a sum over ER, where ER is the electric field on this site, that site, that site, or that site, plus this interaction term, which is the electrons or positrons hopping around the lattice based on whether or not there's an electric field at a site. So basically what happens is the electrons, if the electrons move according to this term, what has to happen is the electric fields around them have to change in order to be able to deal with Gauss's law properly. And that's what UR and UR dagger does, is it basically ends up increasing or decreasing the electric field by 1 unit in order to make sure Gauss's law still applies after they move. The final term is, because this is relativistic, we have a mass term corresponding to the particles. And so the thing that's actually really interesting about it is that the electric field, formally speaking, is unbounded, right? You can have as much electric field as you want in a model in principle. But in practice, we always have to put a cutoff on it so we can actually fit the representation of it inside a quantum computer. The problem is that that cutoff can be huge. And because that cutoff can be huge, this HE term often ends up dominating the rest of these guys. So we ended up using Trotter-Suzuki methods for simulating this because of the fact that if we use Trotter-Suzuki methods, the error scale is like the commutator. And the commutator of this term over here and everything else is quadratically smaller than ER squared. It only goes like ER. So in a case where we have to deal with a large cutoff, Trotter-Suzuki ends up actually giving us, despite its simplicity, better scaling than the optimal method of qubitization. So that's why the structure that we're using to attack this problem. We note that the commutators here are smaller than the magnitudes, and so we use a technique that can take advantage of those commutators, namely Trotter-Suzuki. And so when we go through all of this, for example, is after spending a while on the blackboard, we were able to work out this optimized circuit for simulating the interaction terms or the hopping terms between each of the different sites. The diagonal terms are easy and I won't bother going into them. But this is basically it. The +1 and -1 are qubit incrementers and decrementers. So, you can basically look up your favorite implementation of a Carey ripple ladder or something like that, and then just substitute the appropriate circuits in there. But this is it. And, just in case I haven't intimidated you enough by math yet, here is a theorem that ends up giving the total number of gates needed in order to be able to simulate this for any epsilon greater than 0 and any t. It's a rather gnarly looking mess, but the key point about it is that we end up finding with this particular simulation that we can actually do computationally challenging examples of this simulation using about on the order of 10 to the 14 gates, which is expensive. I mean, if you take a look at present day quantum computers, the best that you could realistically do is on the order of maybe a couple hundred gate operations. So 10 to the 14 is a little bit out of reach at the moment. But if we one day end up getting quantum error correction to actually work, this would actually correspond to, depending on how fast we can end up making the cycle time for our surface code, we could end up doing this in a couple of months to a couple of years. However, this is also, I should mention, roughly about the same cost that our initial studies on chemistry gave us. And as I'll be showing you soon, recent work has reduced those costs by about a factor of 100,000. So the hope is that we can get this down. Now, another downside is the number of qubits that we end up needing for this. If we'd like to be able to do something like this on a near-term machine, well, if I have 10 qubits to store the cutoff, which actually isn't all that many, that is already 1/5 of the biggest quantum computers that we can currently get at the moment. And so this approach, that I gave you for simulating quantum electrodynamics just isn't going to be terribly practical for what we have at the moment. So is there a way that we can do approximately full QED on present day quantum computers? And that's where effective QED comes in. So using this, basically what we did is we just took the Feynman diagrams that ended up describing the propagation, truncated them at second order, built an effective Hamiltonian for that, and integrated over the photon modes. By integrating over the photon modes, now we no longer have to track them. We only, of course, get information now about the electrons and the positrons. But if we're interested in some problem like relativistic chemistry, for example, if we wanted to simulate gold, where we needed to deal with strong relativistic effects, then this theory would be perfectly fine for describing something like that. So in any case, this is basically what we end up doing. And again, we end up finding, after optimizing and doing a very careful analysis of what the commutators are, that for this particular case, the commutators actually work out to give you basically the exact same value for the scaling, it turns out, that we end up getting for qubitization. So this is really cool because it means that we can get the advantage of near-term quantum computers and that we don't need any extra qubits to do this simulation. But we end up having exactly the same performance for this application as these other methods that end up requiring a huge number of qubits. So that's one of the reasons why this approach is very well suited for near-term quantum computing and actually doesn't require any more qubits than chemistry simulations would. Now, for the simple cases that we took a look at, we looked at simulating a relativistic free electron gas. And the number of gates we needed for this, yet again, is 10 to the 14. I don't know what it is about 10 to the 14. For some reason, first time I do everything, it always seems to be 10 to the 14. But that's what we ended up getting for this. And the hope is that by continuing to optimize and continuing to think about this, we'll be able to beat that. So in the remaining bit of my talk, what I'd like to do is I'd like to talk about the other extreme. Those were problems where we had some kind of local structure or some imbalance between the size of the terms that we could take advantage of in order to be able to simulate it more effectively. Now I want to take a look at a less structured problem, namely the problems of simulating chemistry. And so this problem the problem of simulating chemistry is actually an interesting one because depending on who you talk to, chemistry is either easy or it is impossible. Specifically, what I mean that if we take a look at people solving problems in quantum chemistry these days, what they'll often do is they'll do things like, a couple cluster or a configuration interaction calculation. And those things actually run in polynomial time on classical computers. And so from that perspective, that's efficient, and from our perspective, we can't necessarily beat that with a quantum computer. So what's the game in chemistry? Well, the game in chemistry isn't a simulation on quantum computers, isn't to beat these efficient approximation methods. It's to get better accuracy than what these methods can get. Because all of these approximate methods that run in polynomial time make uncontrollable approximations. On a quantum computer, because we're directly emulating the molecule inside the system, we don't need to make almost any approximation in this. So that is the win. But the question is, what's an example of a molecule that we need to have an unprecedented amount of accuracy for? And Marcus Ryer and I spent some time looking at this. This was actually mostly Marcus's idea. I spent the time building a simulation circuit for it. But he proposed taking a look at biological nitrogen fixation. The reason why he suggested this is because basically it goes back to an industrial process invented in 1909, known as the Haber process. And I can't underestimate how important the Haber process is. To give you an idea, right? It single-handedly kept Germany in the First World War by giving them a way to be able to produce munitions, despite not being able to mine ammonia nitrate in their colonies anymore. The next thing is it's used in basically all of present day fertilizers, and now it uses up about 1 to 2% of annual energy globally in just this one reaction. And so you'd imagine, given that kind of importance, right, industrial chemists would have optimized the hell out of this process. You might be surprised then to realize that since 1909, nobody has actually found a catalyst that's industrially practical to do this. And this is one of the reasons why it uses up 1 to 2% of global energy, because we need high temperatures and pressures to be able to basically break the triple bond that holds nitrogen together and allow it to easily react with the hydrogen around it to form ammonia. So it came then perhaps as a little bit of a surprise to people that actually bacteria can do this at room temperature, no problem. They found this enzyme that I've drawn down here, and this is the active site for it. This is known as the iron molybdenum complex at the center of the nitrogenase. The X, by the way, is carbon. I haven't updated the figure. For a long time, it wasn't known. But in any case, this is the molecular knife that's used to slice that triple bond apart to make ammonia. Big problem is that any oxygen whatsoever in the environment will destroy this molecule. And so that works fine inside a cell membrane, which can protect it from oxygen. But in an industrial process where you got to keep costs down, we cannot use this. So the hope was, well, maybe we could figure out how this molecule ends up working, and then we'd be able to synthesize our own oxygen-tolerant versions that would be able to improve this. But one of the reasons why nobody's been able to do this is because we don't know how this works. And the reason why is these approximate methods fall flat on their face. The reason why is that we've got iron and molybdenum in this as well as a bunch of sulfur, which are heavy, heavy atoms inside a condensed area. So all the electrons, they just start spinning around like crazy inside a small little volume. They all become entangled, strongly correlated, and the approximate methods that people have used in the past fail. And so this is this is why this was important, because we were able to finally point to a clear example that people have tried to study for a very long time, but have not been able to actually fully understand because of the fact that very precise calculation is needed. And so since then, this has kind of basically become a standard benchmark problem. And the question is, well, how many gate operations would we need in order to be able to simulate common configurations of this, which would show up in a process of trying to determine the reaction pathways for this enzyme? So the first calculations that we ended up getting for this back in 2017, which made it in, the awkwardly named PNAS journal, required, you guessed it, 10 to the 14 gate operations. So, not to be deterred, we spent years since then shaving off orders of magnitude using the previous methods that I talked about. So these approaches just use Trotter-Suzuki methods. Recently, what we've done is we've borrowed from the chemistry community in order to take advantage of a different way of representing the system. And this approach is known as tensor hypercontraction. And the idea basically is, for the nerdy theoretical chemists in the audience, is to express the Hamiltonian as the two electron term in the Hamiltonian for the Coulomb operator in a form where we can express what would ordinarily be the molecular integrals in this tensor contraction. What we can then do is we can then take a look at these tensors, and then we can do a low rank decomposition of everything, only keeping the terms that are going to be sufficiently important in order to ensure that our approximation error in the end, which I called epsilon THC. By the way, I know some of you might find this amusing. So we called this paper, our THC paper, for the longest time, because tensor hypercontraction, right? Well, we were so disappointed because we were aiming to get this out on April 20th, but we weren't able to get it out until the summer. I know, we missed such a golden opportunity there. But in any case, The blame it on COVID, I guess. The key thing is that once we've done this low rank decomposition, the end of the fourth terms that we would ordinarily have in here can become approximated with a linear number of terms, which is fantastic. Because for most systems, that we only need basically a logarithmic overhead on top of this linear number of terms in order to be able to closely approximate this. This won't hold for all systems, but will hold for many, according to some perturbative calculations that have been done. The next thing we do is even cooler. What we do is we say, oh, well, okay, what if we end up actually taking a virtual space, which is far bigger than the one that we're actually simulating? Then we do a number of Givens rotations in order to rotate our creation and annihilation operators to be non-orthogonal combinations of these orbitals, which may or may not be in the actual system. Then we use this non-orthogonal basis in order to be able to do our simulation and emulate the effects of having a basis that's much larger than the one that we actually get. We go through, we optimize, and we find a much better model for this and to minimize the cost of qubitization, which, if you recall, qubitization ends up scaling like the sum of the absolute values of these coefficients. So we just use that as our cost metric, and we optimize based on that. Then, after spending a lot of time optimizing other features of this, we end up showing that this 10 to the 14 number after this can be improved to be about 10 to the 9 gates. Well, okay, I've taken some liberties with fives, but that shows nearly a factor of 100,000 improvement over the last 4 years, from not just advances in algorithms, but also from borrowing the best theoretical chemistry that we can in order to solve these problems. And so this shows really, an example of a type of problem that qubitization is beautifully suited for. There isn't nearly as much structure for a problem like FOMOCO, right? Where, looking at this, it's really hard to see what kind of physical structure we could take advantage of in the terms to be able to improve the simulation. So we use qubitization and improve the representation and optimize, and that's what gives us our wins. So to conclude, I'd like to leave you with a couple of open questions. And these are mainly kind of like things that have been bugging me for a really long time. First is, I told you that we have like maybe 3.5 different quantum simulation methods that all each are the best at their particular niche. So question is, are there good ways of taking the features of many of these different simulation methods and combining them? So can we find ways of slicing up a problem, and kind of similar to what, for you theoretical chemists like cone-sham DFT, how it can slice up a problem into different parts that you would approximate using different techniques? Can we come up with something analogous where we would do quantum simulation of, say, Trotter-Suzuki for some part, where the commutators are really nice, and maybe use qubitization in another part where they're not? This has been some preliminary work towards hybridizing this has been done by work involving myself, Guanghao Lo, and Vadim Koluchnikov that used multi-product formulas to hybridize between Trotter and linear combinations of unitaries. But the point is that we don't know how to do this generally. The next question is, well, okay, what about our fundamental formulation of quantum mechanics, right? This e to the minus IHT is the propagator of the dynamics. That's really natural if you know what the Hamiltonian is. But in quantum field theory, normally you start with a Lagrangian, and then you work through path integral representation for the dynamics. Is there a way that we can actually drop the Hamiltonian from Hamiltonian simulation and talk about path integral simulation? To date, nobody knows of a way to efficiently simulate quantum dynamics when given from an action perspective on a quantum computer. And that's a major weakness, especially as for this last point that I'm going to get to. A bit of a nerdy thing that bugs me is that time-dependent Hamiltonian simulation can't be simulated in a cost that's additive in a number of bits of precision you need. It's multiplicative in that. Whereas the lower bound is additive, not multiplicative. So we don't know if there's a bit of a gap there. It's a small one, but it would be really great to know whether that gap can be bridged. The next thing is that LCU actually gives us a number of different approaches. Trotter was the most natural thing for people to think about for simulating dynamics because unitary matrices are what quantum computers do for a living. But most of the integrators that we use in numerical analysis aren't linear, or sorry, aren't unitary. So the question is, can we port over more general integrators, and when would those be useful? For example, when might it be useful to use Runge-Kutta integrators over Trotter-Suzuki? And using the methods such as linear combination of unitaries, we can actually realize this. But finally, kind of from a bigger perspective, I think the deepest philosophical question that we still struggle with in quantum simulation is this notion of the quantum Church-Turing thesis, i.e., can the universe be simulated in polynomial time on a quantum computer? And while we've made great progress towards this in terms of simulating quantum field theories and simulating chemistry, we still don't know whether or not the standard model actually can be simulated in polynomial time on a quantum computer. And potentially, by developing techniques like this and continuing along this long path that I've kind of outlined here, it's my hope that we'll not only be able to show that the standard model can be simulated in polynomial time, but also that it can be practically simulated on a quantum computer. Thank you very much.
Thank you very much, Dr. Wiebe. We are open for a few questions because I know time is of the essence. Please, if you have a question, raise your hands or type it into the chat. Sal, do you see any?
Okay, we have 2 questions in the chat.
Okay, go ahead.
The first question, let me get this correct. First of all, this was a great talk. And the question is, why is the Hamiltonian required for quantum computing? What is the difficulty of simulating in Lagrangian directly?
Great question. So let me be really clear. So the Hamiltonian is sufficient for it's sufficient for quantum simulation, but it isn't known to be necessary. All the methods that we've developed so far really have started from the assumption that we know what the Hamiltonian is. I've taken a few tilts at the windmill myself with trying to look at this path integral question. And I've even also been interested in Bohmian mechanics, which I think would be even cooler. But sorry for the digression. The big problem with path integral formalism is you have to sum over a large number of paths. And what ends up happening is the paths that end up having large values or large actions associated with them will tend to cancel each other out. But this ends up leading, using techniques like linear combination of unitaries to sum over all of those different phases. This ends up causing actually an analog of the sign problem to end up happening. And basically what ends up happening is your success probability ends up being nearly 0. So the key problem that we're dealing with is that I think we don't know how to formulate really how to present the information about how to sum over the paths properly in a quantum computer. If we sum over all of them with equal weight, then you run into the sign problem. But that's not how theorists do it. Theorists take a look at this and they have some a priori knowledge about what paths are going to be more important than others. And they can use that in order to be able to get this to converge. So I think the biggest problem for doing this from a path integral perspective is really kind of finding a good way of conveying this intuition that theorists use when they do the calculations by hand into the quantum computer. And to date, I don't think anybody's figured that out yet.
All right, let me sneak another question in quickly. What does it mean to simulate the standard model? Someone needs clarification.
So that's actually a very good question. I'm not sure I fully know myself. So what I mean in particular is, like, let's imagine that we're taking a look at some scattering process for which we want to compute the S matrix. What we would ideally like to be able to do is we'd like to be able to say, compute some element of the S matrix or an expectation value of the dynamics governed by it for two particles and their associated fields colliding with each other and going off. So that would be an example of a particular problem within the standard model that might be interesting. Others, there are questions about ground states that could be quite interesting as well. But really, I don't think that people have quite identified a particular specific problem. The biggest problem is that we don't know how to write down a Hamiltonian for the standard model in a convenient way, or we don't know how to directly simulate the Lagrangian. And until one of those two is solved, thinking about the particular question to ask when before we understand how to approach the dynamics is perhaps putting the cart before the horse, I think.
Right. Noel, do we have time for one more question?
Yeah, I see we have 2 more questions in the chat. Let's just answer that. And if I also left my email address to everyone, if you all have further questions, you could forward it to me and I'll pass it on to Nathan.
All right. Again, the next question is, I love the examples. Are there others you could go briefly over, other examples you could go over describing the state of the art?
Sure. Yeah. So there's been work that's recently been done on some models related to like the the SYK model, I believe, which ends up being relevant for ADS CFT. That's about the most that I can say regarding that. But there's also been a lot of work that's been going into non-Born Oppenheimer-based simulations. So for all the simulations that I showed you in the past in chemistry, we've made the assumption that the nuclei stay put. So there's been a lot of work about dealing with the situation when the nuclei are allowed to move and have quantum wave functions describing them as well. And we've actually been able to find recently that for some of these examples, we can actually get substantial speedups relative to, substantial improvements in accuracy for some systems, either near disassociation or where there's relatively light nuclei. The next problem that I think is that's been creeping up lately, that's been interesting, is simulation of open quantum systems. So I've just been discussing closed quantum systems at the moment, but in general, you end up having, all of your systems, any physical system, it always interacts with a bath that's beyond the control of the experimentalist. And figuring out exactly how to efficiently simulate generic quantum channels is a really important question, and we're really only at the infancy of understanding how to simulate open quantum systems. So those are 2 examples that I can think of off the top of my head, but there's a ton. It's a really broad field and it's rapidly growing.
Okay.
All right, that's it. That's the last of the questions.
Okay. I just want to thank each and every one of you all for attending this this Thursday's Quantum Thursday lecture. Nathan, thank you very much for presenting to all of us. Very informative lecture. And I just want to promote that next Thursday, our quantum lecture is going to be at 12 to 1 p.m. next Thursday. Again, thank you very much, Dr. Wiebe, for being our guest lecturer. And thank you all for attending this meeting. And we see you all next Thursday. Thanks and bye.